This is the beginning of the last few weeks of the AP Physics class. In this case, we're going to start looking at some engineering aspects of physics. In other words, how do people apply physics to some real-world situations? We're going to look at E&M, or electricity primarily, not magnetism. And we're going to build some circuits that do specific functions. Before we build circuits, we have to understand how to power these circuits, how to make these circuits work. And a big part of this is a power supply. We're going to first start with an unregulated power supply, which is a fairly crude power supply, and then we're going to work our way into more sophisticated power supplies until we build a power supply we can use for the rest of our investigations. So the objective of this video is to understand how to design, how to test, and how to completely characterize a very simple unregulated power supply. Our power supply is going to convert 120 volts AC, which is sinusoidal, into 20 volts DC, which is constant. And we have to say approximately here, because we may not be able to get exactly, as a matter of fact, we'd never be able to get exactly 20 volts. So here's our black box. This is actually a blue box, but it generally is called a black box. It's going to accept 120 volts AC, and as we notice here, it really goes, the peak value up here is sitting at about 160 volts, because when we say 120 volts, that's the RMS value of the waveform. And then we're going to produce a 20 volt output, which is much smaller down here, and also it's constant, it's not sinusoidal. We're going to deliver this to a load device, a load resistor, and hopefully it's not just a big dumb resistor that we're using as a power supply, but it's something we're going to actually use that would provide utility, for example, integrated circuits, microprocessors, whatever. So that's basically the setup we're looking for. The first step in this is to get that 120 volts down to something that's a little bit more realistic. And so what we do here is we apply it to a transformer. A transformer is just a mutual induction device that is going to have more windings over on this side than on that side. And so in this case, we're going to drop something that looks like it has about 160 volts peak down to something that looks like it has about 20 volts peak to peak. So we're going to just run it through a transformer. We're still far ways away from a DC voltage or a DC potential, but we made a good first step. So our next step now is to go through and try to get this thing look like a constant value. And we're going to do that in two steps again. The first step is we're going to put a diode in here. And you say, why a diode? Well, we know something about diodes. Diodes have a tendency to conduct in one direction, to conduct current in one direction, and block current conduction in the other direction. So maybe we could use this to somehow kind of make this thing look more like DC. So let's see how that diode, so we're going to look at the diode. This is our test fixture for the diode. By the way, you've done this in a lab, so this shouldn't be particularly exciting. We put the diode in here. This is the symbol for the diode. And then we're measuring the voltage across the diode and the current through the diode. We put this kind of weird battery, and this battery has a knob on it, this conceptual battery. And we turn it this way, we make the potential smaller, including negative. We turn it this way, we make the potential larger, including positive. And then we can get, if we take this voltage and then we map it along here, and then we put this current and we graph it along the vertical axis, we get a picture that looks like this. And we find that when the potential across the diode becomes positive, which is this region, the diode first conducts very little current until the potential across the diode becomes about 0.7 volt. Then it dramatically increases the amount of current that goes through the diode. So this is a non-ohmic device, okay? It does not obey Ohm's law, okay? Because we do not have a straight line here, or a line. If we have a negative potential across the diode, in this case, we would have a big negative here and a positive here. What we'd find is that the diode conducts very, very little current until the potential has to get fairly large. And we're talking about typically tens to hundreds of volts. And then that diode goes through something called a breakdown. where it will conduct current very, very quickly. Okay, if we're going to use it now, we find that what we're doing with the diode is that sometimes during that sine wave, the diode has a forward bias, which is this region. This is your forward bias region. And at other times, it has reverse bias. So let's see if we can characterize those diodes through those two times. When the sinusoid that's across the diode has this negative with respect to its ground, let's assume this is ground potential, we would find that the diode is in reverse bias. It's in this region. And being in this region, we find that there's no current that flows through here. So the amount of the potential across this resistor is just 0. When we go conversely into forward bias, which is this region over here, is what happens is we have a positive, the sinusoid becomes positive, this lead becomes positive with respect to that lead, and we end up with a situation where we have current that flows through here, and we have a maximum of about 0.7 of a volt actually across that diode. That means that the current that that flows through this, if this is R, the current is simply this, and we have most of the potential, this V-in potential, across the resistor here, the load resistor. So given that we have a diode that behaves that way, let's see what happens when we actually revisit our circuit. So the diode, this is the way the diode behaves. This is our circuit. It's sinusoidal, up and down. And then that means in this region, where the diode is forward biased, this is positive with respect to this side, that's what this means, is that we actually have the diode pretty much just pass current so that the potential across this resistor is approximately equal to the input voltage, is approximately equal to this, except we have to subtract 0.7 of a volt. There you go. And so, and then when it's in this region, this is the reverse bias. There's no current that flows, or very little current that flows in through this region, and so we expect pretty much zero potential across that resistor. So if we believe that, then we can then take a look at what this thing looks like. And here we have, this is kind of a power supply that exists now, and we have kind of a unipolar AC, not quite a DC across here. So somehow we need to kind of make this region, we have to flatten out this region in order to do it. Well, when we say flatten out, we need to store charge. We need to store, store charge or store energy between these cycles. And the way we do that, of course, is through our old friend, the capacitor. So we're going to put a capacitor in here. This is an electrolytic capacitor. Remember, this is always positive with respect to this side. And then, so what is that capacitor going to do through here? Well, the capacitor is going to store charge. It's going to charge up here, okay? And then during this time, it's going to discharge. So we get this kind of interesting waveform when we actually put this thing together. And it looks like this. So during this phase, the capacitor is we assume the capacitor starts at 0. So we start, this is the voltage across the capacitor, which is the same, by the way, as the output voltage, is that we charge up, and then at this point, right about here, the capacitor potential is higher than the input to the diode, so the diode goes into a reverse bias. In other words, the diode ceases to conduct current, and now we just have a discharge of the capacitor. The capacitor continues to discharge until the potential reaches a place where all of a sudden this becomes positive with respect to this, and then we repeat that little cycle and repeat the little cycle. So if you want to look at the entire picture during this part, the the capacitor is charging. Through this part, the capacitor is discharging. We reach this part, which, by the way, occurs before the peak in the input voltage to the diode, and then we charge the capacitor again, and then we continue that process. This is actually the same picture. Okay, we just kind of opened it up a little bit, and we notice a couple of things. I don't know if you can see it, but there's a little gray line under here, and that's a sinusoidal input to the diode. And we find the following: the diode pretty much follows. This is the red is the output of the or the potential across the capacitor. The potential across the capacitor pretty much follows the sinusoidal input, except it's always 0.7 of a volt smaller, because that's the voltage drop across the diode. And so then when the diode quits conducting, the capacitor discharges, then we do it again. So we have that. The discharge of the capacitor looks like this. It's an exponential, which you knew that. However, if we assume that the drop in here is fairly small, in other words, the capacitor does not come anywhere near discharging between these periods of the input sinusoid, is that we find out that that this can be approximated pretty much by a straight line. So we have a straight line, we can find the slope of that straight line. So we find here this is where the capacitor goes from discharge to charge, okay, and it goes from discharge to charging. Okay, now this whole thing, this little kind of humpy up and down thing, is called ripple, and ripple is generally something we wish to avoid in a power supply, because we want a power supply that's nice and flat across here. So how do we avoid the ripple? Well, there's a couple of things. One is we can increase the load resistor, but that sometimes we can't really afford, because the load resistor is really dictated by the application of this. We can increase the capacitor value, okay, that would also decrease this. Or the other thing we can do is we can charge it more often. Notice that this is not being charged during this region. Is there anything we can do to charge it instead of every 16 milliseconds, to charge it more often? And if we did that, then we would basically kind of half the ripple in this, or approximately half the ripple. Well, we can do that by playing the following trick. And this is called a bridge, okay? And so what the bridge rectifier does, and this is called a full wave rectifier, is uses 4 diodes instead of 1 diode. In these 2 diodes, the red diodes, conduct when this is positive with respect to this. And so what happens, it charges the capacitor then. The green diodes, and let's see, I'll change the color. Hang on. I'll get fancy. The green diodes, which are this way, will charge the capacitor when this is negative and this is positive. So what we're doing is we're charging the capacitor on every half cycle of the sine wave. If you believe that, or follow that, is that what now the waveform looks like this, and we find that the ripple is approximately halved in this case, under reasonable assumptions. So this is what we generally will do. So we'll use a full wave rectifier in everything except the simplest applications. In order to do that, we can use 4 diodes, or better yet, we can go through and get a package. And so this is a little package that has the inputs for the sinusoid. And on this side, we put the capacitor. And this little package has 2 leads for the sinusoid and 2 leads to hook to the capacitor. And it's as simple as wiring up a diode. And that. So this is a this is a bridge rectifier, and you'll use those in the lab. Okay, so let's design an unregulated power supply. We need some requirements, which would be the input voltage, in this case 120 volts, 60 hertz. The output voltage, in our case, is 20 volts, DC. The maximum output current, this could be a number between milliamps up to hundreds of amps, okay? So it varies quite a bit. And the maximum ripple, how much do you want this thing How much noise do you want? How much do you want from the ideal situation of giving a constant potential output? The design, we need to find a transformer. We need to find a bridge rectifier that would fit and then we need to find a capacitor in both the capacitance, and we need to worry about the maximum voltage that capacitor will tolerate. So that's what we're going to be building in the lab. So before we do that, though, we have a little problem. And the little problem looks like the following. We have a problem because we need to measure things that are about 20 volts in this lab. We have a voltage probe that is less than 20 volts. As a matter of fact, I think our voltage probe, has a maximum input of plus or minus 6 volts. So how do we measure this stuff? How do we record data? How do we do all this stuff? Well, what we're going to do is we're going to put a voltage divider on it. So a low voltage divider looks like this. And so when we want to measure this test voltage, we're not going to attach the probe to that test voltage because that test potential may be too high. What we're going to do is we're going to put it through a voltage divider. So if we look at it, we take the voltage that we're trying to measure, we put it through the divider, which is over here, and then we get a voltage that we apply to the probe, which will be less than 6 volts. Okay? So we can go through now and kind of augment the voltage probe, which is this region, with the divider network, which is over here. Now, the relationship between the test voltage that we're trying to measure and the probe voltage that we're actually looking at is through this relationship. Now, notice I have an R2 prime here. The reason I'm accounting for that is that when we look at the impedance from here to here, it's actually the parallel combination of this resistor and the resistance of the voltage probe. Now, typically voltage probes have very, very high resistance, much greater than a megohm. So in this case, generally this R2 prime is about R2, and we can just get rid of it. But we need to make sure that when we pick values of R1 and R2, we have to be a little careful in a couple of areas. First, the value of R1 plus R2 should be large, so we don't end up changing the test voltage. The other thing is that R2 must be much less than the resistance of the probe. Otherwise, the resistance of the probe would affect the voltage division here. So with those two things in mind, let's go and calibrate a probe. So we're going to build a probe, and we're going to pick an R1 and an R2 here. And the way that we calibrate it is the following. We take some calibration potential here, and we measure, which has to be less than 6 volts, okay, or less than whatever the capacity of the probe is. We put the probe, and then we record it, and record it here. So now we know what the potential of this thing is. Now we put the probe on this, and now we get a different potential, and that different potential I'll call V divide. So this is the potential we measure when we use the divider. Now what we do is we come up with a ratio, which is equal to the first measurement, V cal, which is right up here, divided by the second measurement, V divide. And then what we now know is that when we use this in a test fixture, we're going to get a measurement, and that measurement we're going to multiply by this calibration number that we have up here to figure out what the unknown is on here. So it's a little bit awkward, but it's something we can do in order to test this. Okay, I hope you understood this, because tomorrow you'll be coming in and actually building a power supply. This finishes this video.